Okay, so let's look example 314. And I will preface this example by saying that this is probably the most difficult example in the notes. And I'll probably not ask you anything as difficult as this. And it's not necessarily difficult, it's just sort of a lot of difficult writing. It's a bit weird, like the algebra is a bit difficult to write because there's some weird things in it. But we'll go through it nice and slowly and look at it. Alright, so we're asked to estimate the standard Gibbs or the standard reaction Gibbs energy of the Haber-Bosch process at 500 Kelvin from the value that it is at 298 Kelvin. Right. So then typically what we use for this case is we can use the Gibbs-Helmholtz equation, but the Gibbs-Helmholtz is only going to give us a value or going to help us really at a specific value. So we're going to need to integrate the Gibbs-Helmholtz equation to give us another equation that we can use to calculate the Gibbs energy at a higher temperature. Right, so that's essentially what we need to do. Okay, right, so how do we do that? So let's start with the fact that we can write the Gibbs-Helmholtz equation in the form of equation 335. So that is writing it as, oops, not in the highlight form. So that is something that we can say, we can write dt of delta G over T at constant pressure is equal to minus delta H over T squared. Right. So in other words, if we're looking at reactions, that means we can just rewrite this in a form for the reactions with all the bells and whistles that we all love to write out so nicely, is equal to minus delta of reaction over T squared. Right. So that means we can write the Gibbs-Helmholtz equation in this form. But I'm just going to use the shorthand. So you know that delta G and delta H represent that for the reactions. So I'm not just so we don't have a messy notation. Okay, so we're using this form. Now essentially what we want to do first is we want to write it in a differential form so that we can integrate that differential form so that we can work at two different temperatures, right? So just to explain what that basically means, let's say we had a parameter A, right? And if we wrote dA, that means we could then say between some initial and final, they would have dA would be equal to delta A, given that A is a state function, right? So then we could calculate a delta A, which we could then write as A at the final is equal to A at the initial plus whatever A normally is equal to. Okay. So that's actually what I want to get to. So I want to take the differential. So I'm just going to wipe out all of this. So I want to take the differential of the Gibbs-Helmholtz equation. So this thing on top here. I want to take the entire differential of this. And you can see where it sort of gets messy because there's already a delta in there and whatnot. But let's work with that. Okay. So if we take d of delta g over t, okay, right, that then gives us d dt of delta g over t, which is still fine, but then also 2 dt. So that's the same as what we had, for example, if we wrote u is equal to, what's it, pdv or whatever, then we would have something p and then just a dv, for example, just next to it. So this is like the p part and this is the dt part. So you see this pops out again, but of course there's a partial differential that we have, and then we have the dt part. So just as we used the fundamental equations with the Maxwell relations, as such, we're writing out this part again. Oh, we have that part. So that's the left-hand side. Of course, this is at constant pressure. Actually, you should just write that in. Okay. Then the right-hand side. What does the right-hand side look? Well, the right-hand side is minus delta H. There's nothing here to be concerned about. That is just dt. Okay, that's just get slapped on at the back. Okay, so that's its exact differential. All right. So from this point, we must then integrate. Okay, so if we integrate this thing, what does that become? Well, that becomes delta g over t, right? So in other words, it's the change into g over t, and that is equal to the integral. I just need to keep my bearings. So the minus goes into the front, so this minus there, and I'm just first we're going to call the two temperatures Tc and T, which we're going to integrate between. So then we have delta H over T squared dt. Right. And this delta H is defined at which temperature? It's defined at Tc, because it is the Tc. So Tc is for the 298, and then the 500 is just T. So that's how we're defining it. Okay. So just to remind us what it is. Okay, so this one can easily be rewritten. We can write it out a bit further. So the minus delta H can go to the front. T, we have 1 over T squared dt. What's the integral of 1 over T squared? Well, it is minus T, so minus delta H Tc 1 over minus 1 over T between Tc and T, that's equal to minus delta H Tc. Substitute in those values, so then it is 1 over, let me still remember to just write it out, so 1 over T minus 1 over Tc. It's your basic rule, so then we just, okay, let's take out the minus, so then this becomes plus delta H Tc 1 over T minus 1 over Tc. Okay, and add all the way, so that's equal, let me just bring this down, so that's delta G Right. So we have an equation to calculate the change in delta G over T, so which is equal to that right hand side. Okay. Now let's just write out the left hand side. So delta, what does delta G over T actually mean? Delta, that means we have, so remember we have a T and a TC, so that then means delta G at T, which is the 500 Kelvin, 500 Kelvin over T, minus delta G TC over T. So you see that's the delta. We just made it explicit in the sense that we said the two G's are the ones that are dependent on whatever they are. So remember, that's essentially now saying delta RG standard molar at 500, and that's essentially saying delta RG molar at 298, right? Just the shorthand that we're using, and that is equal to delta H TC, so you get the shorthand, right? 1 over T minus 1 over TC. Right. And then we just want to get an expression to calculate this value, right? Because we're interested in this one. That's essentially what we want. That's what we're asked, to estimate the standard reaction of Gibbs energy at 500 Kelvin, because that's exactly what this is. The standard molar Gibbs energy of reaction at 500 Kelvin. So we just want to get that alone. So in other words, we multiply through by T, so then multiply everything with T, so then we get delta G T minus delta G TC is equal to delta H TC. 1 T over T is equal to 1 minus T over TC. Take over that, take over our delta GTC there, so delta GT is equal to delta H just realized I made a little boo-boo. See, I'm also human. I know it's shocking to believe. I think this should actually be TC. Yeah. So it's over T and over TC. So this should still be over TC. And then there should be a T here. Aha. Yes. Okay, so this small mistake. So let me just go over that perhaps again. Alright, so we were there. So what did we calculate? Delta G over T. We were calculating that. So we substitute in T and TC. So in other words, where all the, so the T subscript, T and TC and TC. And then you subtract the 2 and this side the same thing. Now we're multiplying through by T. Okay, so we multiply through by T, so then we get delta GT minus T over TC delta GTC. Yes, okay. Delta HTC 1 minus T over TC. Then we just take this one across. So then delta GT is equal to T over TC delta GTC plus delta HT Tc times 1 minus T over Tc. Okay, so then we have a way to calculate what we want to calculate, which is the Gibbs free energy at 500 Kelvin. Okay, so we just need to plug in our values. So I just need to, I think it would be prudent to write this out. So delta G of T is actually delta M 500 equal to, okay, so T is 500 Kelvin over 298 Kelvin. Delta GTC is then 2 times the formation energy of, or the formation Gibbs free energy of ammonia. Alright, because remember there's 2 moles of ammonia gas that forms, and I mean, we've been over those kinds of examples 14 million times. And the formation energy of your reactants in this case is 0. So in other words, products minus reactants, it's just the formation energy of the product that's applicable here. And then same for the enthalpy. So in other words, we have 2 times the formation enthalpy of ammonia and that is times 1 minus 500 over 298 Kelvin. Okay, that is 500 over 298 over, let me just quickly jump over to ClickUp. We remind ourselves where to get our resource section. So of course, as always, it's under the useful materials or the resources. So there's ammonia gas. So ammonia gas's enthalpy of formation is minus 46.11. So that is 2 times minus 46.11. It's kilojoules, so both of these will be in kilojoules. So that's minus 1 minus 500 over 298. And then, of course, we're also interested in the Gibbs energy. I just had it, ammonia gas, minus 16.45. 2 times minus 16.45. Okay, and it's plus those 2 values. So 500 over 298 times 2 times minus 16.45 plus 2 times minus 46.11 times 1 minus 500 over 298. gives us 7.31 kilojoule per mole. Right. So, I think, the basic, the end was quite easy. I think the most difficult part is essentially just this first part, trying to develop a way of calculating the change. But you can get the change from integrating your equation 3.35, which then will give you the change of the change, so to speak. And once you have that, it's just basic, straightforward integration. All right. This example I will quote again. It's very difficult and it's not that important. It's not really the focus of this theme. Okay.